Okay, I think we are just going to get started there. So what I'm just looking at the screen now, and what I'm going to sort of see, yeah. So we're about to kick off here. So my name is Kevin O'Brien, and welcome to another whyr webinar. And what we're going to do is. Sorry, I'm just going to pause this a second. I'm just watching the playback loop. So what I'm going to do here, sorry about that, folks. So my name is Kevin O'Brien, and sorry about that. So what we're going to do is welcome you to another whyr webinar. And this week we have J.Mount and N.Zumel, and they are the authors of Practical Data Science with R. Just if you're actually watching us on YouTube, you could actually have just a quick look down below on the YouTube channel there, and you actually might see the details about the abstract. What we'd just like to draw your attention to is that there is, for this week, there is from Manning Books, there is a special discount offer that you can look at right on the top of the description for this presentation. So what we're going to do is I'm just going to sort of introduce, sorry, I'm just freezing here. I just actually taken this off the video. So what I'm going to do is actually introduce Dr. N.Zumel and J.Mount from Vtreat. I'm having a panic attack here. I'm very sorry. I'm just going to bring this back up to where I have it. And I'll just introduce them. And sorry about this, folks. Now, we'll get it back. So just actually, N.Zumel is a principal consultant with Vtreat, a data science consultancy in San Francisco. She has a PhD in robotics from Carnegie Mellon, and with J.Mount is one of the authors of Practical Data Science with R, a popular text on data science. And also, we have J.Mount, who's also a principal consultant with Vtreat and also one of the co-authors. He has a PhD in computer science from Carnegie Mellon. So sorry about that, folks. And both of them have maintained quite a few open source R packages and Python packages. Sorry for being clunky there. Thanks for joining us, folks. Just actually, so as a bit of fun, what we're very interested in is your questions. So if you want to read your questions or write your questions, and leave them in the text or the chat on the side of YouTube. We'll keep track of them as we go. We'll pick out a few for the end of the presentation. And also, as a bit of fun, you can actually just sort of tell us where you're from, because we love seeing where people are from. We noticed that there's quite a few from Peru and Malawi and Kenya, and that's great. We're really excited about that. So sorry about that, all that. So what I'm going to do is hand over there. Sorry about the clunkiness. So I'm going to hand over now to Nina and John, and let's just get started straight away. So I think we're good to go.
Okay. Thank you, Kevin. This is Nina. Hi, I'm going to share my screen now. Okay, ready to go. Thank you very much. First, I'd like to thank Marcin for inviting John and I to come and speak here at whyr, and I'd like to thank Kevin for that really nice introduction. I am N.Zumel, and J.Mount and I are consultants, as he mentioned, are consultants with Vtreat LLC, a data science consultancy in San Francisco. And today we are talking about advanced data preparation for supervised machine learning. So kind of the outline of the talk. First, we're going to talk about the problem itself, which is preparing data. And I'm going to sort of motivate why you want to prepare data at all. What are the issues that we are worried about? And I will give an example of trying to do machine learning modeling with and without data treatment to kind of highlight the data issues that we're concerned about. Then I'm going to go on and talk about Vtreat, which is our package, John and my package, for automating variable treatment in R. R is the original implementation, and that's the one that I'm talking about today. There is also an implementation in Python. Some of the data treatments that we're going to talk about may potentially introduce some biases into the modeling process. So we're going to go on after I've discussed Vtreat to talk about how we mitigate some of those potential modeling biases, and then we'll conclude. So let's start with, why do we want to prepare data at all? Well, as I'm sure all of you have probably experienced, real life data is very, very messy. It's got a lot of missing values. It's got a lot of invalid values, a lot of unexpected values, sometimes misformatted values. And generally speaking, having real life data, that data requires a lot of massaging to get it in a nice, clean format that can be accepted by standard machine learning algorithms. Now, some of those data preparations that you have to do will be problem specific or domain specific. So for example, if one of your input variables is a reading from some instrument, you have to know something about the domain in order to know what are valid readings, what are readings that are in a valid range for your problem, what are readings that are likely to be noise or misreadings or just glitches. However, there are other kinds of data issues like missing values that tend to be more generic, and they show up over and over and over again from problem to problem to problem. And you tend to deal with them the same way from problem to problem to problem. And those more general data issues are the ones that are good candidates for automation. And that's what Vtreat does. Vtreat is a package that automates the treatment of rather generic data issues so that you, the analyst, and you, the data scientist, have more time and more energy and more brain power to spend concentrating on the more important problem-specific aspects of your modeling or machine learning problem. So some of the typical data problems that you might expect to see are things like bad numerical values, missing values, which are generally marked as NA in R, or not a number. Infinity, if that happens to show up, can often be a problem as well. With categorical variables, you can also, again, have missing values in your data. Another issue that you can have with categorical variables is that you might just have too many levels in your category, which I'm going to refer to as high cardinality categorical variables. And the problem there is that typical machine learning algorithms represent a categorical variable with k levels as k or k minus 1 indicator variables. So really, a categorical variable is not just one variable, it's many. So if you have a very high cardinality categorical variable, you actually have far more variables than you think you have. And that sometimes causes computational problems with machine learning. Another data problem that we're going to address is the problem of having invalid category levels. And by that, I mean, if you have a categorical value variable in your data that shows a certain number of levels and your training data only recognizes those levels, once you fit your model and you get new data, if a new categorical value shows up that you didn't see before in your training data, that can cause your machine learning model to crash. And so Vtreat tries to mitigate that problem as well. So to make this a little bit more concrete, we'll actually do an example problem. The example problem that we're going to do is the data set that we're going to use is the data set for the KDD 2009 Data Cup competition. And the task in that competition was to predict account cancellation, which is also known as churn, from the supplied input variables. Now, this particular data set is problematic in a lot of ways. It's a very messy data set. Among other issues is the fact that when the company who gave this data to the KDD gave it to them, they obscured the names of the features. So the column names of this data are all nonsense. The level names of the categorical variables are all nonsense. So people in the competition were not able to take advantage of any actual domain knowledge they might have had to do things like feature engineering or feature selection. They just have nonsense inputs that they have to try to learn a signal from. Other issues with this data is there's a lot of missing values, and we'll get a little deeper into that later in the talk. And there's a lot of high cardinality categorical variables, which, as I mentioned, also can be an issue. And it's also challenging because this is a rather unbalanced task. The churn rate in this data set was about 7%, which means that the positive instances that you're trying to learn are relatively rare in the problem. So how about we just jump right in? We're going to take this data as it is, and we're going to try to model it with a gradient boosting model in XGBoost in R. And so we're just going to take the data as it is, and we're going to try to feed it into XGBoost and get a model. And the first thing that you're going to see is that it's just going to crash. And the reason that it crashes, the first reason that it crashes, is because the data set that we have has string valued variables for the categories. And XGBoost in R does not accept string valued variables directly. You have to convert them to numerical representations first. And that's relatively straightforward, but even if you fix this, you're still going to run into other issues. As I mentioned, this data has a lot of missing values. It's a lot of blank holes. If you look at all of the variables in this data and you count how many missing values there are in every variable, you'll see that on average, about 70% of the values are missing. That's over half of them are missing. And in fact, the median missingness for this data set was 97%, which means over half the variables in this data set are mostly blank. That's a challenge for machine learning. And in addition, there are also many high cardinality categorical variables. The median number of levels for a categorical variable in this data set is over 1,200. And some of the variables get up into the tens of thousands of levels. That is also a problem. And of course, when you have very large variables like this, you will inevitably have the problem with novel levels that even if you manage somehow to fit this model, when you try to apply it to new data, assuming that the new data was distributed in the same way, you're going to run into levels that you've never seen before. And the model is likely to crash on a lot of data. So how do we try to fix this? Well, let's talk about a kind of an ad hoc grab bag solution. You can try to use model matrix or fast dummies or other encoder packages in R to convert the string valued variables into a numerical representation. You can try to use mice or another imputation package to try to impute reasonable values for the missing values in this data. You might try to do something fancy, like maybe use a Keras embedding layer to try to deal with those high cardinality categorical variables, try to find a less complex representation of them that is easier to model with. You can try to do all these things, and if you get it done correctly, it might work okay. But the fact is, it's a lot of steps to manage, and it's a very ad hoc process, which means that it's going to be somewhat difficult, or at least tedious, to have to implement because you're doing it by hand. And more importantly, perhaps, it's also going to be tedious and difficult to maintain going forward. In addition, some of the data treatments that I've talked about might be rather complex, which means they may be rather statistically inefficient to try to deal with safely, and also means they're possibly subject to model bias and potential overfit in the models. So let's try to find a better way. What we are advocating, what we are recommending, is the use of Vtreat, the package in R that does all of the data corrections that we've just talked about in one step. It's very easy to use. It's just a matter of calling one or two functions. It has known good performance. John and I actually developed Vtreat for use in our own data science practice. So we have actually used Vtreat with a lot of clients very successfully, and we know that it works well. Vtreat also has citable documentation. There's a paper about it on archive.org. So those of you who are doing modeling and analysis in an academic or scholarly setting, and you need citations for all of your data processes, that is available. And even though I'm not going to talk about it today, Vtreat is cross-platform. The original implementation is in R. There is also an implementation in Python. And it is also possible to directly treat data directly in a SQL database, either through R or Python. So let's go back to that KDD problem. And now we're going to try to do it with Vtreat. We're trying to treat the data with Vtreat and then model. So the function that we're going to start with is this function called make cross-frame C experiment, which I acknowledge is a very clunky name, but that's the name that it is. And this function takes as input the training data, the names of the input variables, the name of the outcome column, and the value of the positive instances, which in this case is 1. So in this problem, the outcome is either 1 or -1. 1 means churn, -1 means not churn. You put all of that into the function, and what you get as output are two objects. You get something that we call a treatment plan. And a treatment plan is basically a set of instructions for how to treat data in the future for this problem. And you get a treated training data set. This data set is guaranteed to be completely numeric with no missing values. So then we take this treated training data, and then we can put it into XGBoost. And I'm skipping a couple of steps here that are not completely relevant to this discussion. If you want to see all of the code for this example, it's on GitHub at this link below. So you can see the whole thing and even try to run it yourself. But at any rate, here we have the training data, and we put it into XGBoost. And this time we can successfully get a gradient boosting model for this churn problem. And what I've got on the right-hand side is the results of that model on a holdout set. And in the original competition, the metric that they used to evaluate the competitors was AUC, or the area under the curve of the ROC curve. So that's what we're also going to use as well. So the result is Vtreat on the very first try, completely off the shelf, by which I mean we use Vtreat with all of its default settings. We use XGBoost with its default settings and no hyperparameter tuning. We get an AUC performance of 0.74. By comparison, the contest winners, it was a multi-day contest. On the first day of the contest, the best performance among the competitors was about 0.75. And that got improved by the end of the contest. The winner got a result of an AUC of 0.77 about. So we didn't quite get winning performance, but the point is that we got in the ballpark of first day best performance within minutes on the very first try, which means that we've got a lot of time to try to tune and improve our results by doing, more clever things like hyperparameter tuning on the machine learning algorithm, maybe additional steps, feature engineering, and so on within our modeling pipeline. Vtreat basically gives you a very solid and reliable platform to start building on, where you no longer have to worry about all the data cleaning and data munging, because that's all been done for you. And you can start doing kind of the fun stuff, the interesting machine learning stuff. So that's the example of why you might want to use Vtreat. So let's get a little bit more detail about what it actually is. So the goal of Vtreat is to faithfully and reliably convert messy real-world data into a ready-for-machine learning format that is entirely numeric and has no missing values. And by ready, we mean that it's a simple format, a simple data frame that is compatible with linear models, tree-based models, and neural net models as they are implemented in R. By faithful, we mean that we have preserved as much of the relevant modeling information in the original data as possible through the data treatment. And by reliable, we mean that we have avoided a number of sort of subtle modeling biases that might have been introduced by the data treatment process. So here is kind of the process of using Vtreat. There's actually two ways of doing it. And this is kind of our recommended way, the way that I just showed you with the KDD example. And it starts with one of these make cross-frame experiment functions. There are different functions. There's a family of functions that you use the appropriate one for whether you're doing classification or regression. The input to this function is your training data. And the training data creates a treated model training data set, which is completely numeric with no missing values. The variables that are in the treated data are a little bit different from the variables that are in the original training set. There's new variables that have been derived from the original training set, but it's essentially the same information. And in addition to that training data, the make cross-frame experiment also creates a treatment plan, which is a set of instructions for creating the new derived variables in future data. You take the new treated model training data, and you use that to train a model, and that produces the model for your problem. And then during the model application phase, you have new data. This is your application data. You take it and you treat it with the treatment plan via a Vtreat function called prepare. And that creates a new treated test set or treated application data set. And you can use that with your model to make predictions. So it's very straightforward. There's actually a second way of using Vtreat, which is a little different. And this is a way that you might consider if you have a very, very large training set, a training set that is large enough to partition into two subsets. And I'm going to call those subsets the calibration set and the training set. And the way you would do it here is there's a function called design treatments. And again, this is a family of functions. There's a different one for whether it's classification or regression. And it produces only a treatment plan. So you take your set of calibration data and you use it to design a treatment plan. Then once you've got the treatment plan, you take the treatment plan and your other subset of data, your training data, and you prepare it to create your new treated model training data with the new derived variables. Use that to train your model. And then the test application phase is the same as it was in the previous case. This way of running Vtreat is a little bit computationally faster than running it the other way. But because you're only using part of your data to create the model, it's also somewhat less statistically efficient. So we generally, if you have a big enough data set to partition like this to get a good treatment plan and get a good model, this is a good, somewhat faster way to run Vtreat. Otherwise, we recommend using the make cross-frame experiment function that we showed on the previous slide. And another thing that the treatment plan contains is an advisory table that we call the score frame. And what the score frame shows you is the mapping between the original variables in your data and the new derived variables in your treated data. This particular example is not the KDD example anymore. This is a smaller, simpler example from the Vtreat documentation. And here's a link on the bottom to the Vtreat documentation on GitHub. So you can look at that. In this smaller example, the original data had 3 variables, x and x2, which were numeric, and xc, which was categorical. And all of these 3 original variables were turned into multiple derived variables of different types. And this code column tells you what type they are. And I'm going to get a little bit more into that later on. Different types of derived variables. And in addition to having given you this mapping of what your variables are and where they came from, you also get some advisory information about how potentially informative these new variables might be in your downstream modeling. So here we have a column called R squared. And what that is the R squared of each of these variables when fit to a single variable linear model to the outcome. So the intuition is when the R squared is larger, that means it's potentially it's more likely to be an informative variable in a downstream model. The sig column is the significances that are associated with these one variable models. And that's kind of the opposite thing. The smaller the significance value is, it means it's more likely that these variables are going to be informative. One other thing that Vtreat does is that it compares these one variable model significances to some default threshold, and I'll get into the default threshold in a little bit. And those variables whose significance who appear to be more significant than this default threshold are marked as recommended. So that's Vtreat's assessment of recommended variables are those that Vtreat thinks are the most likely to be informative in downstream models. And the ones that are not recommended, where recommended is false, are those variables that Vtreat thinks are likely to be noise variables. So you don't have to use that information, but basically you can use this recommended column of the score frame as advisory information if you want to do a little preliminary variable selection before going into your model. And why would you even want to filter them out? Well, you may not want to. Most machine learning algorithms are tolerant to a small number of noise variables. They should be able to just ignore them on their own. But if you have too many noise variables, especially if you have too many noise variables relative to the number of signaling variables, this can degrade the model fitting process because the noise will begin to, the machine learning algorithm will not be able to distinguish the noise variables from the signal variables. So in particular, if you have a situation, a problem where you have a lot of variables that you're looking at, and you actually suspect that really only a few of them are informative, you may want to consider some sort of variable filtering, whether with Vtreat or some other way. The way Vtreat does it is that it calculates a default threshold that's set to try to allow only one noise variable per derived variable type into the recommended set in expectation. So basically, if this worked perfectly, all of the noise variables except possibly one for every type would be filtered out. And then we mark recommended the true, the variables that pass the threshold. I'm not going to get into how we calculate that default threshold right now, because that would make this talk way too long. But if you're interested, that's also in the documentation. If you look in the documentation, and here's the link, there's a section called the deriving the default thresholds. And that tells you how the reasoning behind the simple calculation that we do. And the default threshold is, it's designed not to be too strict, because you don't want to accidentally filter out important informative variables. It should be noted that the heuristic that we use to figure out recommended assumes that these one variable models, looks at these one variable models in a linear model, as a linear model. It looks at these variables as they behave in a linear model. So you might accidentally filter out variables that are informative in a very nonlinear way, or that are primarily informative in interaction with another variable. So there is a risk there. But this was a simple filter to be able to implement, and we have found it useful, and you may possibly find it useful as well. Okay, so that's kind of the goals of Vtreat. So let's get a little bit into more detail about what the derived variables that Vtreat creates are. What does Vtreat actually do? Okay, so the first thing Vtreat does is it fixes bad or missing numeric values. So NAs, not a numbers, infinities. It takes all those missing values in the numerical variables, and it replaces them with a harmless stand-in. By default, that stand-in is the mean value of that variable. But you can use any single variable or one variable summary statistic. So if the mean is not what you want, if you have, for example, log normally distributed numerical data, you might not want to use the mean as your stand-in. You might want to use the median. You can do that. You can use the min, you can use the max. You can also use just a constant like 0 if that is more suitable for your problem. And that's all user specified, but by default, it's the mean. And in addition to filling in all of the bad values with the stand-in that you pick, Vtreat also adds an additional indicator variable that we call the isBad variable to mark where these substitutions occurred. Adding this extra column makes this data treatment invertible. And so it assures us that we're preserving as much of the information that was in the original data as we possibly can, even after the treatment. Another interesting thing about having this isBad indicator is that in our own practice, we've kind of noticed that in business settings, missing data is often an indicator of where that data came from and how it was processed. So for example, if you have data that's coming into you from 2 different channels, some data from one channel may have a certain attribute, and that attribute may not be available from the other channels. So you're going to have missingness in your data just there. And it's often the case that where the data came from is an important piece of information. Sometimes it's even more important than what the data actually is, what the actual values of the data are. So this missingness indicator, this isBad variable, is consequently often one of the most informative signals that you can use when modeling. At least that's what we found in our own practice, and we've had colleagues that have backed this up. Kind of as a side note, Kabikoff in his book R in Action, which is from Manning, so with your 30% discount, you can pick up R in Action if you like. He refers to these as shadow variables, and he makes matrices, shadow matrices of just these indicator variables, and he uses them to do sort of more sophisticated missing value imputation than what we do. So if you're interested in that kind of thing, that's also there. But we do simple, very simple missingness imputation. The second thing that Vtreat does is it encodes categorical levels as indicators, and this is pretty straightforward. It's very similar to what model matrix will do for you. The main difference is that Vtreat keeps information about what the levels of the categorical variable that it observed are, so that it can recognize and handle situations in application where it sees novel levels. So as a concrete example, suppose we have some data, and one of the variables in this data is the state of residence of the subjects of this data set. And let's say that they all come from the western side of the United States, from the states California, Nevada, Oregon, and Washington. So when Vtreat encodes your data, it will encode this categorical variable as 4 indicator variables, one for each of those states. And then, you go ahead and you do your modeling and you're fine. Then when you have that model, you want to apply it to a new data set. You need to go and treat that new data set. And whoops, it turns out one of your subjects is from a state, Wyoming, which was not in your training data. Under normal circumstances in R, this would often crash the model. But if you're using Vtreat to treat your variable, then it will catch that and simply encode Wyoming as all zeros, basically no level. And then it will continue to run. The other difference between what Vtreat does and what model matrix does is that by default, Vtreat only encodes the most common levels that are available. So rare levels, and rare is something that is user defined, are not dummy encoded. They're not encoded as indicator variables. And the reason that we don't encode all the variables by default is that you want to control the unboundedness of having a very large number of dummy variables when you have high cardinality categorical variables. So a good example of a high cardinality categorical variable is something like postal code. So in the United States, there are something like 40,000 postal codes throughout the United States. There are something like 3,000 just in California. So if you had a data set where you were trying to model, I think this example was modeling home sale prices or something like that. And one of the variables you were using was the postal code that that home was in. And you were just doing it even just for the state of California, you would potentially have 30,000 variables just from postal code alone. And having that many variables, or having a very large number of variables like that, can be a problem, a computational problem for many machine learning algorithms. So you want to kind of reduce the number of variables if you can to just kind of the most common ones. And another problem is that you will, if you have that many high cardinality variables, then you will almost with 100% probability, when you try to apply this model in the future, you will run into a postal code that you didn't see in your training data. It's almost inevitable. And that's another problem that you want to mitigate. So to manage high cardinality categoricals, by default, Vtreat only dummy encodes levels that occur more frequently than 2% of the time, or in at least 1/50th of the rows. And you can change that threshold up and down. You can even change it to 0 if you want to actually encode all of the variables. And this, as I said, prevents kind of having a dummy variable blow up, because by default, you will only get at most 50 indicator variables per categorical variable in your set. And in fact, in practice, you will actually get far fewer than that. In order not to lose all of the information about those rare variables, Vtreat also converts the categorical variable to one single informative numerical variable that we call an impact coding. And people in Kaggle competitions also do something similar, and they call it target encoding. And how impact coding works, it's basically just a lookup table. You take your training data and you make a lookup table of the average home, if home price is the outcome that we're trying to predict, then you'd make a lookup table of the average home price for each postal code. And then you also look at the average home price over the entire data set. And then the impact variable is the difference between the global average home price and the home price in that postal code. So what you end up with is a single numerical variable that is negative for postal codes where the home price is less than the global average, and positive for variables where, postal codes where the home price is greater than the global average. And that's why we call it an impact. So we're talking about this as this is the impact of this postal code on home price. And then once you've learned your lookup table, your impact code, then it's very straightforward to impact code data from there on. You just take the postal code variable and you just map it to the appropriate number using your lookup table. And then zip codes that postal codes that you've never seen before, novel levels, simply get mapped to 0, which is basically the same as saying, I have no information about this particular postal code. So I'm just going to assume that the average home price in that postal code is the global average home price. Now, one very important thing about trying to do something like this impact code, we found it to be very useful, but it's a little bit dangerous as well, because you have to be very, very careful not to use the same exact data to learn your lookup table and to train your downstream model, because this introduces some undesirable bias. Basically, what happens is that you've now leaked information about the outcome into your training data. So it makes that impact coding variable look too informative to the modeling algorithm, and it will tend to pay more attention to it and potentially ignore other more truly informative variables. And you will end up with a model that is overfit to the training data and will not perform as well on future data. So the safe way to do impact coding is to either split your training data into 2 sets, the calibration set and the training set, use the calibration set to learn your lookup table, your impact coding, and then use that impact coding to encode your training data, and then use that training data to fit your model. If you don't have enough data to do that, then you want to use what we call cross methods to simulate having 2 separate sets. And this is a good place for us to switch speakers. So I am going to hand it over to John. I'm going to stop sharing my screen right now.
Yeah, so this is J.Mount, and as you can see, most people would rather have their throat slit than follow Nina in a presentation. She did a fantastic job, and I'm going to look stupid, but I'm going to go ahead and do my part and share my screen. Sorry, just 1 second. There we go. So Vtreat has many purposes for many people, and really the impact coding was one of the ones that stuck out the most, and it's the one that took the most work to get right. And so if you do it wrong, like use the same data set to design the treatment and then use that data set as your training data, you end up with what's called a nested model bias. And this is something that data scientists have to be sensitive to, that basically it's okay to use models in parallel, but whenever you use them in series, you get this data leak because each model, when it's trained, looks at both outcomes and inputs and then confounds the two somewhat. So the methodology we're using to avoid this issue and let us use the same data both for experimental design and for purposes is called cross methods. And this is one where you're going to say cross methods, we've always used them, or cross methods, we never use them. Basically, it's cross-validation style techniques for a goal other than cross-validation. So cross-validation is when you evaluate or validate a model on data. Cross methods are a larger, more general category when you use simulated out-of-sample data to simulate having more data. So this is the diagram. And I'm going to slow this down and explain what a cross method is. So basically, in our notional data set, we have 6 data rows. Each one has the explanatory or input variables, which we're coloring in green. And then also the outcome, our dependent variable, which we're coloring in blue. The cross method looks like this, which this should be completely illegible. So let's slow that down. Here's our data again. Now we'll just assume that this data is in a shuffled order. Therefore, the first third is a valid random subset. And we're going to break that into thirds in that way. Again, we assume we shuffled while doing this, of course, keeping in the outcomes with their explanatory variables. And the very first thing we do is we use 2/3 of the data to train a model in general, or in particular for Vtreat, we use 2/3 of the data to design the impact codes. Then only the third of the data that wasn't involved in the construction of those impact codes is scored through that model. That model, so then we have for the first 2 rows, or the first 1/3 of the rows only, what are their proposed impact codes? We then throw that model away and repeat the process for the next third. So the 2/3 that are complementary to the middle third are used to build a new impact coding system via Vtreat. And then those 2 rows or third rows that weren't in the construction of that encoding scheme are then re-encoded. And we repeat it for the last third. So if what we were doing was saving the model quality instead of the model predictions, this would be called cross-validation. But we're saving the model predictions. And again, in our mind, the model is Vtreat's encoding to impact codes. So this is called a cross method. All 3 models are thrown away, but it maintains the invariant, which will be true for later application data, that no row was transformed using a transform it was part of the design of. That's something that's going to be true for future data. So to simulate future data, we make it true here. So that's a cross method. Now, we've said the reason you use them is without cross methods, impact coded variables lie about their degrees of freedom. For downstream modeling, a 50,000 level impact or string valued variable is really 50,000 columns, but it's all hidden in one column. And so it's really 50,000 columns. So it looks a really good predictor because what it did is it memorized the data. For instance, in Nina's housing example, if there was any houses that were unique to a zip code, then their price is exactly the delta price of that house from the grand average. It's actually a memorization, but the downstream system doesn't have any way of knowing that. However, in the impact coding scheme, a house that occurred uniquely in only one training example, for every example it's not in the training set of, it gets coded as missing. And for the one it's in, there's no code. So it again gets coded as missing. So it gets thrown out. So it really fights the overfit. One thing we ran into that was hilarious is once you try to fix something, everything's your fault. And this is why, as Nina described, Vtreat's variable filtering is minimal. It tries to let all the variables through except for the ones that are obviously noise, because we figure downstream models can handle variable selection. It's just Vtreat is making more variables, so it's its fault if it overwhelms the downstream system. It might seem a little off just to use a mere linear method, but remember for these categorical variables that we're impact coding, it's a linear method over a join table, so it's actually a very arbitrary, powerful function. So it's actually quite a thing. Now, again, under the spirit that if you touch something, it's your fault, cross methods can also leak data all by themselves. There's a one, I've written on this a couple times, it's called the leave out one leak. But basically, the problem is when you're using cross methods in your cross frame, which you can use for training, the impact codes are no longer a function of the input alone, they're a function of the input and the cross-validation ID. And that means they may leak. However, again, Vtreat has systems of getting this right and not dealing it. In particular, we don't use leave one out cross-validation because that's the most extreme version of the leak, but there's a number of mitigations it takes. Now let's reel that back in. Things are not that complicated or dire. If you use Vtreat, you're going to get correct performant behavior because our 40-page paper and the people we've consulted with, we've worked out how to do this right. And not in a mysterious how we do this right, but here's the documented why this is right. But this is Vtreat from the user point of view. The thing we don't want you to do is design treatments on a training data and prepare on the same training data. The latest version of Vtreat issues a warning if it detects that. So really, from a user point of view, all you're trying to do is avoid a warning. The 2 methods Nina talked about are the calibration set method, where you've split your training data into 2 subfamilies, calibration and modeling. You design your treatment plan using only the calibration data. The calibration data is never used for anything again. And then preparing your treatment, preparing your data for training, it just looks like preparing any other data. Or you use the cross-frame method, which returns both data fit for training and a treatment plan fit for later use, such that they're sort of jointly independent of each other to the extent they can be. In all cases, when it goes time to use Vtreat, you merely call prepare treatments and test. So this is the conclusion. The value of cross frames, and we really appreciate how long you spent with us on this talk, but here we're getting to the end. The value of cross frames. Naive, suppose we do it wrong. We use the exact same data for designing the data transform and for building our training data. Here's our training set performance on the KDD 2009 thing. We get an AUC of 0.98 on the training data. Now, if you're an experienced data scientist, you know that performance on training data is only a stand-in for actual model quality, and good performance is a big fear factor, that this should be red flags. And sure enough, on test set, this model has an AUC of 0.6. Then it's abysmal. Now, Vtreat, when used in the correct method, either the cross frames or the partition, this time we use cross frames. Here, we get performance on training data of 0.81. Now that's definitely overfit because we know the winners were in the 0.77 range, but it's in the ballpark. The model's behaving on the training data similar to how it may behave on later data, which means decisions made on the training data might be correct. And some of this overfit could be XGBoost, not Vtreat. And sure enough, this composite model, when applied to held out data that Vtreat never saw, it basically has an out of sample performance of 0.74. Again, I think this is rounded off, but it's in the ballpark of the winning solution, which is way better than 0.6. Because remember, with most score, it's how much of the deficit are left. So 0.6 is 0.4 away from perfect AUC of 0.1. 0.74 is 0.26 away from the perfect of 1. So you've really made a substantial improvement at that point. So in conclusion, Vtreat is an easy to use, statistically sound process. It's documented, so if you don't want to use the package, you can use the methodology. Its prepared data is entirely numeric and without missing values. So it's ready to go into XGBoost, ready to go into neural net. It's no substitute for getting your hands on the data. It's trying to save you time to do that. It's saying the data is going to wear you out on simple issues that are easy to fix, so you can't do your actual work of domain engineering or joining in external data sets. It's trying to leave you that time. So it's automating what can be automated so that you have time to do the valuable data treatment steps. And again, here's some references. Basically, the impact coding, as we said, Kagglers call this target coding. Actually, we think impact coding is slightly more resistant to overfit than target coding because if done right, a conditional delta actually doesn't overfit and leave one holdout, though a target encode will. So we have some references there. Basically, scikit-learn's contrib package is added target encoding, which is kind of nice. The R Vtreat package is up on CRAN and GitHub. And the Python pandas version of Vtreat is available in PyPy. And thank you very much for your time, and thank you very much for hosting us on this. And let's see. Yeah, get back to Kevin, please.
Is it back to me now? Hi there, folks. Thanks for that. Thanks, John, and thanks, Nina. That was a great talk. Actually, I found it really fascinating. I hit all the main points that of all the things I would sort of deal with myself. I'll just actually read through a few of the questions I have, actually. So one actually there is just actually came there. I'll just work with the one that just came there recently from Samuel Carter. Can Vtreat handle multiple distinct data sets, or do data sets need to be combined in some way prior to treatment? So
I'll take that.
Yeah.
So Nina does most of the mathematical design of Vtreat and the research. I do most of the grungy engineering. Unfortunately, Vtreat is assuming there's one data frame. So you would have to join them up before or join them up after. So Vtreat is not smart enough to deal with multiple data sets, and that's my fault.
Okay, good stuff. Actually, from the same contributor, Samuel Carter, just actually earlier on, he asked, how does Vtreat handle calendar time date data like POSIX, CT, and stuff like that? Actually, or just can it, or?
Yeah, it's unfortunately Vtreat considers all variables either numeric or string valued. So
Yeah.
It would convert it to a time sense epoch. So it would not do, again, it doesn't do anything special for that, though I could see a lot of things one might want to do special for times.
Yeah.
We would sort of, I think Nina is often used to teach poor man's dummies that you might want to blow a time variable up into hour of day and minute and make some derived columns on your own. But very good question.
Yeah.
Yeah. Or if it works for your problem, you can often do time since reference time. You'd like a simple reference time. So if you're doing if you're modeling the change in something from a start date, then you can just sort of do the subtraction yourself and say days from start date, which turns it into a regular number. If that's possible for your application. It's not always.
Yeah, like I think she's talking about cohort age where start date's varying. But again, you'd have to do that yourself, unfortunately.
Oh, great. Good stuff. So actually, just another one actually that was asked earlier on by April Smith. Essentially, I just actually recall the question. It was like, is the Vtreat feasible for use with the tidy data format or the tidyverse? How does Vtreat interact with that if you're sort of using dplyr and stuff like that?
Well, since it's engineering, I'll go ahead and take that if that's okay with you, Nina.
Yeah.
Vtreat assumes a data frame. So to the extent a tibble is a data frame, it will work with that. It's pipeable in a dplyr sense because the first argument to the Vtreat functions is the treatment plan, which is exactly what you want for the typed dispatch. So I would say it's compatible.
Good stuff. Yeah, yeah. That's great. And I think there was another one that follow on there. It's just like something, another similar sort of question from Willie Tadema. I hope I pronounced that right. It's just actually sort of with regards to sort of maybe a sort of a comparison between, let's say, recipes and tidy models, or how with regard to Vtreat.
Well, again, recipes and tidy models are frameworks.
Yeah, yeah.
Vtreat's an all-in-one step. So if you wanted to automate, if you wanted to capture what Nina was describing, ad hoc steps, you would use something like tidy models to bind them together, or you might use Vtreat as a step in tidy models if you had it obey its interfaces, which again, it should obey all dplyr interfaces. However, use the tools that work for you. And the idea is that Vtreat's fairly atomic, which means you can combine it with other things. However you want to organize your work, hopefully it doesn't interfere, to be honest.
Great stuff. Yeah. Just another one there was asked there just there recently by just a moment ago by Florian Schmall. I hope I pronounced that right. First of all, thanks. First of all, he says, do you have a rough estimate on computational speed of Vtreat on different types of data, different dimensions of data?
I'm going to leave that to John. Have you done any of those tests, John?
It's a really good question. Yeah, I apologize for that. It's very fast. Its design goal was to be faster than the downstream modeling that follows it. Obviously, the impact coding is essentially an R aggregation. So we tried to make everything vectorized. Vtreat is written in R, not in C, but we tried to use only vectorized functions so that it would scale with data quite well. And it does actually use the parallel package if you allow it. So its design goal, it takes a little bit of time, but its design goal was to be faster than almost any downstream modeling you're using. So yeah, it's a good question because it is the one that's dealing with a lot of high cardinality data.
Good stuff. Okay, there was just a couple of questions there regarding missile value imputation and stuff like that, and mean and median imputation. And it was just actually just the sort of the general theme of it was, can you do different types of imputation there if you are looking to do something a bit more complicated?
You can use, you can customize the imputation for every individual column if you really wanted to do that. The limitation is that it has to be a single variable summary. So you can't do imputations that take multiple columns into account, which you might want to do, but you can't not do it in Vtreat. So basically, like I said, mean, median, min, max, you can write your own single variable function and use that if you want to. You can use a constant if that is appropriate. But one of the other design principles that we didn't talk about is that we're trying to minimize the amount of modeling that Vtreat itself does. You do the modeling, we do the data treatment. And so to us, multiple variable missing value imputation is a little bit of modeling. So we ourselves don't do it. But I think it would be compatible to do it maybe ahead of time and then feed our data, the data into Vtreat for further treatment if there are other things you wanted. So no, we do only very simple imputation.
Okay.
But it's customizable.
Yeah, actually, Nina hit on a design principle that Vtreat has, and why we think it is compatible with frameworks, other frameworks, is anything that involves more than one variable, we define as modeling and stay away from it. Because you need the full flexibility of a framework to say what you're going to do to variables jointly. And we think that's really served us well because it gives us a very well-defined boundary that there's always one more useful thing you could add. And if it's about joint variables, that's literally our definition of modeling.
Good stuff. This next question is more of a bit of a plug. Vtreat is not your only R package, actually. You've actually got quite a good a repertoire of R packages there. And one I'm a fan of myself is wvplot. Not so much a question, but tell us a little bit about those, because I really love wvplot.
Okay, I guess I can take that. wvplots is a convenience package on top of ggplot to create plots that we use over and over again in our practice. So basically, these are mostly data science related plots. So that ROC plot that you saw in our talk, that was a wv plot. We can do plots for double density functions to analyze the distribution of classification scores for a classification problem. We've got, fancy scatter plots. We've got shadow variable plots. We've got plots that you can do. You can compare empirical densities to theoretical ones and all that kind of fun stuff. We're not the only one. There are actually several packages like us that are built on top of ggplot, but these are the ones that we use over and over again and we find really useful. So we just put them out there for other people to use as well.
That's great. Yeah, that was so. Just to be clear, the ROC plots was wv plots, and it's all up on CRAN, and it's well worth a look. Actually, I really like that one. There's one more question that just came in there from Paul Prue. Does it look at, presumably, does Vtreat look at whether a numeric factor is symmetric? So I can't really parse that any further. Unfortunately, is the question clear?
It doesn't really look at the distribution. Correct me if I'm wrong, John. I don't believe it does very sophisticated distribution analysis on numeric data.
No, I think you hit it on the head. It for numerics, it stays away. So I think he's saying, does it do a nonlinear transformation like taking absolute value? And no, Vtreat does not propose numeric transformations. That it attempts just to get them through on its own. So I think I got the gist of the plot. Does Vtreat propose interesting transformations on numeric variables? And deliberately not, though. Obviously, it does complete transformations on string variables, so it does think a little differently about those, to be honest.
Good.
Basically, the value here would be that if you have Vtreat, you can at least fill in all of the missing variables in a numeric variable, so that if you did want to do analysis or transformations on it, then now you don't have to worry about what happens if I pass a na into my transformation function, because sometimes that causes a problem.
I have some really sympathy for that question, because I could imagine a version of Vtreat that applied a generalized additive model to each and every numeric variable on the way in. That would be kind of fun. But just for reliability, we don't call that, because there's always some corner case you're going to blow up on at scale.
Okay, I think we're run out of, or we've got through quite a few questions, so I think we're just on the hour there. So I think we'll probably leave it there, actually. And apologize to all the folks at home. I had a bit of technical issues that was completely self-inflicted at the start. Just to remind you again that there is a 40% discount code for practical data science with R. Just if you look at the description on the YouTube channel there, and well worth a look at. And also, you know, that quite a few of the other packages that are featured on your blog, winvector.com. Is that correct?
Yes, thank you.
Yeah, winvector.com. So that's great. I think I'll hand it over to.
Actually,
I'd like to thank you all. Thank you both for coming. You're both over in the US there, and that's great. I think we'll leave it there, folks.
We'd like to say thank you, and we also like to say that Kevin is brilliant. He looked into the delayed stream, which, if you've ever seen this, there's no way to look away once it's happened to you. So thank you very much for having us.
Yeah, I just had to figure out how to do it. I thought I had a very good setup, and then it just.
Oh, you did a great job. Thank you.
Yeah. All right, we'll leave it there. I think we'll hand over to Marcin and to.